this is an advice for you. If you try to calculate all the information the power information um, in the circuit, for AC circuit especially, please remember that you convert this one into RMS first. So this part should be converted into RMS. So here you see that first one we have current in sinusoid form, and you need to convert the current in frequency domain, and make sure the magnitude over here, you try to use magnitude of not magnitude, you try to use RMS value. Okay, what Hadif did over here, just try to convert first and then use this value to calculate all the information, all the required information. Okay, now how do you get this one? What is this 5? Oh, you try to do source transformation. Okay, right. You did source transformation. Okay, the strategy to transform the circuit from current supply into a voltage supply is correct. So you just multiply the current and also the the impedance, and in this case the impedance look for the transformation purpose is this 5 ohm resistor, or over here we have 5 ohm resistor, and he multiplied these two to get a voltage value. And later he tried to convert the inductor into its reactance value. So here conversion is J, yes, correct, 1 points over here, and conversion of capacitor to its reactance value, or XC, yes, it's J5, and this conversion cannot be done unless you know what is the value of the omega, and the omega can be collected, or you can get the value of omega according to the sinusoid form of your current or of your voltage, also can, when you try to convert it later on during the conversion. Okay, anyway, the omega should be equal to 200 in this case. Okay, this two is correct, so 2 points. And to get the total impedance according to this circuit, the total impedance should be 5 plus 3, and then plus G minus G5. Yeah, this is also correct. The impedance should be 8.94 with angle of negative 26. In my solution over here, I don't have the value of my Z. However, if this is a correct value, suppose that using this, I don't know why. Okay, why you calculate this part, IR1. I don't know why you calculate this part, but basically this part is redundant. But if you look at the next line for IT, yes, you need to use the voltage that you convert over here in phasor form and divide it with the value of your total impedance, your total, we'll call it Z total. All right, now suppose that the value over here is 3.16 with the angle of 56.57. Okay, the problem over here is that Hadif uses the maximum or the peak value of the voltage and as well as the current to calculate the total current. So here 4.47 is the value of maximum and also peak value of the current, not the RMS value. But I think for this part, I can consider that you will have, you will get full marks on that, because it's not necessary that we convert from peak value or maximum value to RMS value up until this point. But in the next thing, I mean, the next calculation where you need to use the RMS current, so that one, I think based on Hadif answer over here, I will deduct some marks. Anyway, over here, I will consider this one is correct lah, up until I total. And of course, the angle of the total current also correct. But I'm worried that why you have this one? Okay, I think you don't need to. Okay, this is a series circuit, means that whatever current flowing here is the same current flowing here. I mean, the same current flowing in each element. And why do we have this one? So my comment is that this part is not necessary. From here, I can say that Hadif didn't, not have a full understanding of what's going on in this circuit. Because actually this is a series circuit with a series circuit, we know that current will be the same throughout the circuit. And I don't know why we have like current, Kirchhoff current law over here. We have like I total equals to I R1 plus IX. I see. Okay. This is for to calculate. Okay, to calculate I and using I total. But basically, this is wrong. You are correct up until this point, from top up until I total over here. You are correct. However, this part, I think I cannot say. I don't know what is your understanding about the circuit. Since you have a look at the circuit over here, from parallel connected current and also resistor over here, you convert it into this arrangement. You convert it into a series circuit. So why you are looking at this circuit anymore? Just focus on this one. So from this circuit, you know that the current that the total current flowing in this circuit is the same current as IX. So you don't need the part that you calculate over here. This is wrong, and the understanding also wrong over here. But up until this one, it is correct. Okay, Adif? Okay, what's the answer for the power? Do you have the answer for AC power in the circuit? Okay. Means that you missed these 3 marks lah. How do you want to get full mark if you didn't calculate? Anyway, this is just exercise, right? Because I only see the IX. What do you mean because I only see the IX? Can you respond on that? Because I really need to change, to to make you have a full understanding about the circuit. Because if you look at the circuit over here, of course, now we have um, series parallel connection. Yes, of course. And when we convert this part, okay, when we convert the parallel connected of current and 5 ohm resistor, you will end up to, you will get this circuit. So in this circuit, we have series connected element. So and again, this is also different. If you look at the first one, we have current. The second one, we have voltage. So whatever calculation that we have over here is regarding the voltage. And why do you still looking at this one? So that's my question actually. When I try to understand this, the part that you have on your right hand side. But anyway, um, um, the one that you have on your left is totally correct. And of course, uh, I think I'm gonna be lenient this time around. If you didn't convert from RMS into from peak value into RMS value, then that is fine for this part. However, for the second part, for the power calculation, you need the RMS information, RMS current, RMS voltage, and so on. So that's why it's very important that you convert it in the beginning. So that in general, for the first part, it's okay. For the second part, later on, I will deduct some mark if you finish that part lah. All right. Please remember, guys. In order for us um, to calculate the frequency domain circuit, I mean, when you try to calculate or analyze your circuit, please make sure you convert from this peak value into RMS value. That would reduce the possibility of doing doing wrong in the next portion of the question. So make sure all the calculation in RMS. Don't calculate your answer or don't analyze the circuit in a peak value. Although it is, I think, it's not totally wrong, but it is to lessen the possibility of doing wrong in the next calculation, especially in power calculation. As you know, if you would like, if you try to use a formula like P equals to VI cos theta, the voltage and the current in that equation or in that formula must be in RMS. So that is very crucial. If you calculate in peak value, you need to use other formula. You can refer back in the lecture notes that I provided. So make sure if you try to analyze a circuit, put it in what you call it RMS value. Then you will be the possibility of getting a wrong answer will be a bit lesser, unless you don't know how to answer it. Means that you don't get any marks lah. All right. Anyway, that's from Hadif. Anyway, thank you, Hadif. But next time, please make sure if you try to analyze your circuit, make sure you change this value or the supply value into its RMS value. Don't just put it. I know it is correct, but please do. Please take the RMS value in order for you to get a correct answer for your AC powers later on. Okay, never mind. Based on Hadif's answer, actually he managed to capture all the values over here. I'm not very strict about the values. I try to focus on your strategy and the way you get that value. So that is more important to me. in terms of value, if you have like a different value in terms of decimal points compared to me, then I should be okay with that. I know because of the conversion of polar to rectangular, sometimes you might consider like different decimal value compared to my solution. All right, and to finish up the question, if you look at the second part of the question, okay, the second part of the question asking about active reactive power in the circuit means that you need to calculate value of P as well as value of Q in your circuit. And I believe the fastest way or the easiest way to do that is by using this formula or using the formula of complex power, where we, according to this circuit, according to the circuit that we have earlier, we have a series connected element and also a voltage source to supply um, the power to the circuit. And we will use this voltage, and also we will use the current information. And the equation that we will use is that we will use this complex power equation where S equals to V I conjugate. And I, in this case, is Ix or I total in Hadif answer. It's okay. But make sure you put the conjugate value. And remember, to calculate the power, you need the RMS value of voltage and RMS value of current. That is where Hadif made a mistake just now, because he didn't convert from peak value into RMS value. So the equation over here might be a little bit different, because you know that this RMS is coming from V peak divided by square root of 2, and I RMS is coming from I divided by square root of 2. So this formula cannot be used for peak value. You need to do some modification. Please refer back your lecture slide that I provided earlier. So now, if you have your RMS value, and I think the best way is to use this formula, the complex power formula. Why? Because from the complex power formula, we can easily multiply voltage and current, and the result of the multiplication, which is in polar form, if you convert the polar form into a rectangular form, you may find that the real part is the active power, and the imaginary part will be your reactive power. And the reactive power, if you try to write down again, define back your reactive power, you must include the negative value over here, because based on the conversion or based on the result of your complex power, you have a negative angle of your complex power. And also, when you do the conversion, you have a negative sign in imaginary at the imaginary part. So in other words, I would like to say that reactive power is a negative value. So negative for us over here. Okay. Any questions so far? Any question?
No, Doctor.
Okay. Can we proceed to next question? Yes? No? So far, okay. But make sure don't do the same mistake as what being described just now, because it's how I can tell it. It's like a silly mistake. I mean, unnecessary mistake, because you got the strategy right, but there's a small portion that you you miss that one, and it makes it will results that it results on you not getting a full mark on that. So please make sure you didn't do that later on your test or in your final. Okay, I think I will skip question number 2 first, because maybe this one is not maybe uh, not significant in terms of your test 2. Okay, maybe later on, if we have time later, I will explain on question number 2. But of course, this question is also important in terms of when when you are facing your final exam. Okay, we try to focus on question number 3, because question number 3 might be involved in our test 2, the one that we see in question number 3. All right. Okay. In this question, if you look at the question, basically we have about what over here? 18 plus 6 is 24 marks. And definitely this one is coming from final exam. 24 marks is quite big mark over here. All right. Now, according to AC circuit in figure 3, we try to calculate the total impedance. Okay, total impedance of Z means that total impedance looking from the source. And we try to solve I of t, IR of t, shown in figure 3 by using source transformation. So I of t and IR of t means that we need to write down our answer in sinusoid form. This is very important point here. Please remember that if the question asks about like this, find Ix, there is no bracket of t, means that Ix is in RMS value, or maybe you can write it in a polar form or rectangular form, and of course it is an RMS value. And if you have question like this, solve current I of t with a bracket of t, means that you need to present your answer in sinusoid form. Okay, this is the pattern of question, but if you cannot present the answer in sinusoid form, does not mean that you're gonna lose all the marks, but you cannot get full mark lah on that. All right, solve the current I of t. I of t is over here. Maybe we try to annotate a bit. Oops. Okay, I of t is here, and IR of t is current over here. Okay, let me ask a little bit about the current. What is the current flowing over here? Can someone respond to me? Is it IR as well? Can anybody respond? Hadith, 0. Yes, of course, 0. Why Hadith 0? Why it is 0? No component, it is open circuit. Okay, yes, correct. Because this one is an open circuit connection. Open circuit. Although I label it as VR, this is a trick for you guys. See here, VR is basically voltage across this and this element, the total voltage over here. And the if looking at the question itself, basically, I can also write it like this. Only one resistor with the value of 3 ohms. But I separate it to make you confused. I mean, to put some like tricks to you guys, so that you can identify which the element itself, the voltage drop, and so on. Okay, let's erase this first. Okay, anyway, the VR over here is basically voltage across 2 ohms and 1 ohm resistor, the summation of that voltage drop. Okay, and finally, we need to prove that VC equals to VR. What is VC? VC is a voltage across here, across the capacitor, and VR is the voltage across these two resistors, both resistors. Means that, of course, if you look at the circuit, the connection over here, we have a parallel connected elements. We have capacitor, and over here, and the second branch, we have resistor. So according to parallel connected definition, okay, voltage over here, let's say we put it as V, is the same voltage over here. So you need to prove that these two voltage is the same. Maybe some students feel that this is a very difficult question because we have proof over here, but believe me, this is something that you already done it over and over again. Okay, we get into the first question first. Right, where's the answer? Yeah, okay. Right, first one, we need to calculate the total impedance. And as I mentioned before this, that the part that we see over here is an open circuit connection. Over here is open circuit, okay, where we have VR labeled like this, an open circuit. So if you didn't include that one also can, because it's just an open circuit. And the Z, or the impedance that we try to calculate, is with respect or looking from the source. So it's over here actually. Is that looking from here, or this on this drawing like this lah. And as usual, if you see that the components over here still in its original value, please convert towards or please convert it into its reactance value. So now we have inductor 1 Henry converted into ZL, which is J4, and we have 0.2 Farad converted into its reactance value, or ZC, which gives us negative J 1.25, if I'm not mistaken, because point is missing over here, 1.25. And both basically is the unit is ohm over here. Both are ohm in the units. Maybe I try to use different color because very similar to my answer over here. All right, now looking at the circuit, you know that these two, okay, these two should be calculated based on parallel connected values. So that's why you see here that we have ZC in parallel with 3 ohms here. And I have simplified it into this circuit, all right? So you may find that these two can be combined. However, to combine these two, you need to use parallel connected calculation. And later on, when you combine ZC and 3 ohm resistor, you may find that these two is in series. So you can also combine it one more time, where when you combine, make sure you use a series combination of, series combination of elements. So Z1 to get Z2, it is basically from given by Z1 plus J4. And when you finish with that combination, and when you finish with that one, the series connection of Z1 and J4, maybe you can label it as Z2 or whatever you like. And finally, you can get the total impedance by combining these two parallel connected elements. So in other words, to get Z total over here, Z total is given by 4 in parallel with Z2. Okay, and I'm not going to discuss detail on the calculation over here. I think you can do it later on. What I'm trying to discuss here is the way you simplify this circuit until you get your final value of total impedance, or your Z. The first one, you need to see that these two can be combined to become one component, one element. Then later on, when you simplify that circuit, you see that these two also can be combined as a series connection. Later on, you can get the total impedance by combining these two parallel connected elements. Okay, that's for the first part, or for the impedance. And the value that you have over here is basically the total impedance, Z total, right? Okay. Now, for the second part, you need to use source transformation in order for you to solve I and also IR. Okay, looking at the question back, right? These two elements, maybe I erase this one first. These two elements can be converted into like this, into a series connection of voltage and 4 ohm resistor. 4 ohm resistor. And make sure that when you try to convert from parallel connected elements into a series connected element, please make sure that the terminal that you are looking at, so in this case, we are looking at this terminal, okay, connection from this terminal up until this terminal. So we only focus on that part only. So the rest, okay, we still keep intact with the circuit. So in this case, we have the second part on the right hand side, where we have inductor over here connected, and also the one that we have over here is the capacitor and also the resistor. Maybe I combine the two resistor into one resistor, and this value should be 3 ohms. Okay, and the current that we are trying to calculate is the current over here. Okay, and the current here, which is considered as I, can be found if you know what is the total value of your impedance in the circuit. So that is what happened in the solution. If you look at here, we convert from parallel connected current into what do you call it, into series connected voltage and resistor. Let me see back the value over here. Is it 20? Should be 20. Okay, 5 times 4. That's why maybe you will have question later on. Okay, if you look at my solution here, hey, why this one we can use the peak value here. Maybe I erase this one first. If you look over here, this is based on 5 cos, if I'm not mistaken, 5 cos 4t ampere and 5 cos 4t ampere. Maybe you will ask, hey, before this, Dr. Hatta said that we need to use RMS, but here why we use BP? Okay, you need to be clear now. For me, I prefer RMS, but if you look at the calculation itself, it doesn't matter whether you use RMS or BP. That is in terms of finding the current, finding the voltage drop, and so on. However, if you would like to calculate your power, you will need the RMS value of voltage and current. So that's why I prefer that this the value of voltage and current in the circuit to be calculated in RMS value. But if you calculate your circuit in terms of voltage and current in peak value, it's okay. You still got the what do you call it, the correct value. I mean, you still got it right. However, for power, later on you will have difficulties in terms of using the correct formula to calculate power in AC circuit. So in other words, this is also correct, but if you convert this value into RMS value, I also consider that one also correct. And can you get what I'm saying?
Yes, sir.
You can either use both. You can either use peak value or you can either use RMS value. However, please be careful in the calculation of power, where in the calculation of power, you need to use RMS value. At this point, yes, it is correct because we don't involve any power. So later on, if the question asks about power, you need to readjust it back, or you need to present your voltage and current in RMS value. Okay. All right. Let's proceed with the peak value over here because we did not done nothing wrong over here. The strategy is that in this question, we need to use source transformation. To use source transformation, we have a look at the part where we have let's see, where we have current in parallel with the volt in parallel with resistor. Then we convert this part to be into this circuit. So we have voltage in series with 4 ohms resistor, and the value of voltage over here, you can easily get the value by multiplying with the value of resistance that you have in parallel earlier. So at this point, voltage can be easily calculated and the circuit itself should be transformed into a series connected circuit. Okay. Try to calculate the value of impedance, which is Z. Why? Because with the value of impedance Z over here, or the total Z total over here, we can easily calculate our current I over here. So Z total is given by 4 plus Z2. What is Z2 is basically? Z2 in this case, if you look at the circuit, we need to simplify this one first. Actually, Z2 have been calculated earlier, where Z2 is Z1 plus Z4. So you don't need to calculate Z2 this time around because it's been calculated earlier in the first part. So what you need to do, maybe if I'm the student over here, I'll try to redraw the circuit. Okay, this is my Z1, Z1. This is J4, and this is my 4 ohms resistor. And later on, I try to reduce it back into Z2, where Z2 is J4 Z1 plus J4. But if you have your own idea on how to solve this one, maybe Z over here coming from, let's say, you cannot use this one because we transform. Okay, Z total cannot be used. Maybe you have your own idea because you see over here, Z total can easily being calculated based on this circuit. You don't need to combine these two and later on combine with 4. In other words, I would like to say that this circuit is basically not necessary at all. You can just use this equation where Z total is given by 4 plus G4, G4 plus Z2. Okay, don't need to use this equation basically. You can also, or you can always have a look back at your circuit and find what is the correct answer for your Z total. Anyway, once you find, once you got the value of your Z total, you can easily calculate the value of I over here because I over here is basically your I total. And see here, yeah, the advantage of using peak value. Here you can calculate your current using the Ohm's law, where this is your V and this is your Z total value, and at the end you will get your current, which is this one is basically I peak value of current, not RMS. If you have converted the value of a voltage in RMS earlier, you need to multiply it again with square root of 2 in order for you to write down your I of t. So here, since we didn't put any conversion from peak value to RMS value, and we consider this one as our peak value, we can use this value straight away into our sinusoid equation. So that is for I of t. And for IR, okay, for IR, we need to use current division. Okay, looking at the circuit itself, you have like elements like this, and later on we have resistors, and in middle here we have capacitor, and here we have the voltage source. Okay, and the current IR is over here. And currently, we did the calculation of I, and using the current division, we can easily find what is the value of IR over here. If you look at the solution here, to find IR, let's say this is ZC, okay, this is R, okay. IR is given by ZC. We take the value of components in opposite branch. We should divide the component with the summation of ZC and R, and we multiply it with current that coming before the branches. Okay, current over here. So I will be divided into these two branches, so we focus on this branch only. So IR can be written as ZC divided by ZC plus ZR times current over here. So that is what happened in this calculation. So we have ZC, which is negative J1.25 divided by ZC plus R, which is R is 3 in this case, and times the value of current. And in this case, current I, again, this is in its peak value. I peak value. And at the end, you will get the value of your IR. So this is IR, and the value or the magnitude that you got over here is the peak magnitude, or the value of the peak value of IR. And since you have the peak value of IR, you can straightforward or write down your use that value to write down your answer in sinusoid form. Okay. Now we move into the third question. The third question says that we need to prove that VC equals to VR. And again, it is simple strategy that we use over here, where we know that since we have a parallel connected elements, the voltage which is in parallel should be equals the same value. So now we need to calculate VR, where VR, according to this one, coming from IR times R. So this is VR. And this is VC. VC should be IC times ZC. So that's what happened over here. We have VR equals to this value, where to get this value, we need to multiply R times IR. Okay, and we can also write down the VR of t in sinusoid form. Okay, since if you look at the question, you might find that we need the value of VR in sinusoid form, because we have VR of t in the question. So you need to write down this one, and you can either use voltage division method. Okay, here we use the voltage division method to prove that VC is equals to VR, or okay, this is by using voltage division, or you can use the one that I mentioned just now, where VC can also be found by using IC times ZC. I think this strategy is much more easy. However, we don't have the information of IC. We need to find IC first, where IC can be calculated using this equation, I minus IR, because if you look at the branch that we have resistor over here, we have capacitor, and we have current coming in is I, and we don't know what is current of IC over here. What we have is the current of IR. So we can use this Kirchhoff current law in order to get IC and use this IC to calculate VC. And you may find that VC also equals to the value of VR in this case. But if you look at the solution that I have here, this is a different method, also can be used to answer the question. According to the solution that we have over here, it uses voltage division method. And how do we use voltage division method? Okay, if you look at the circuit back, okay, we have resistor, inductor, and maybe I try to simplify this one as Z1. Z1, right? Before this is Z1. Okay, this is the voltage. Okay, we will use voltage division rule based on this circuit arrangement, where we have this one is 4, if I'm not mistaken, this one is G4, and for Z1, if I'm not mistaken, before this, it is what? Z1 0.44 minus, okay, this is Z1 0.44 minus J1.06. So the value of Z1 over here is 0.44, 0.44 minus J1.06. This is for Z1. Okay. And looking at this solution, if you like to find what is the value of voltage over here, the V is basically the same value of VR and also the same value of VC. Okay, because we have a parallel connected element that I mentioned just before this. Where is it? I didn't mention over here. Maybe, oh, okay, here. VC and VR should be the same value. So we can say that if we find what is the value of voltage over here, it's the same value of VR and the same value of VC. And according to this equation, we have VC, let's say, I put it like where? I put the equation down here. VC, also V, can be found by using this equation. Z1 divided by 4 plus J4 plus Z1 times the voltage that you found over here. V, maybe I label it as VS. VS. The VS is basically the voltage over here, which is, where is it? Okay, 20 with the angle of 0 degrees. Maybe I'll write down here. This is the value of VS is over here. Okay, 20 with the angle of 20 degrees. And again, if you use the peak value of voltage, of course you will get a peak value of voltage at the end. So the peak value of voltage can easily be used back in order for you to use to write down the equation in sinusoid form. And you see here the voltage VR of t and VC of t is the same value. So this is how we prove that one. But this is one way. The other way that I'm suggesting is that we can also use the strategy as well. This one. We can also use this strategy. it depends on which one you prefer. This is maybe I'll say is method. Oops. Okay, method 2. Okay, method number 2. Maybe you can use this one as well. Don't because the question itself just asking about proof. You can use your own preference of circuit analysis in order to prove that VC is equals to VR in that case. Okay, any questions so far? Can you follow the solution? Can you follow the solution so far?
Yes, Doctor.
Okay. Right, now we get into our last part, which is the question number 2. Okay, basically question number 2 is the same that we found in earlier in Tuesday class, where we are given with parallel connected AC networks, and we have load 1 and load 2. Maybe in our example last time, we have 3 loads connected, all connected in parallel. So in this case, we have 2 loads connected in parallel. The first load, we have 3 kilowatts. Okay, we have load 1. It's something which is look like this. Okay, this is the parallel connected load. The first one, we have P value, P1. And also we have power factor. And the second load, over here, we have synchronous motor rated at 1.6 kVAR. So this we will have Q, which is 1.6 kVAR. And we also have the power factor over here. Maybe I try to write down power factor as including the values over here. 0.6 lead. Oh. And since this is a leading power factor, means that the value of VARs over here, or the value of your reactive power, should be a negative value. That should be not included in the question, but you need to bear in mind that this one should be a negative one because of we have a leading power factor. And this part, we have a lagging power factor, which with a value of 0.8 lag. And we don't have any information of our reactive power. But what we have over here, that we have the active power, which is 3 kilowatts. 3 kilowatts. So based on this information, you need to calculate total active power, total reactive power, apparent power, and also the power factor, total power factor. So for the solution, okay, as I list or as I sketched earlier, we have 2 loads. The first one is load 1 having active power of 3 kilowatts or 3000 watts, and we have power factor, which is 0.8. And bear in mind that this power factor is a lagging power factor, so that's why we have theta, which is a positive value. And from load 1, if you focus on load 1, we can easily calculate what is the value of our apparent power. Okay, maybe I annotate a bit. This one is our apparent power. Apparent power, and this is our active power or real power, and this is our power factor, of course, where you know that P is given by VI cos theta, and VI is basically S, so S cos theta. And if you bring the cos theta on the left hand side, you will get your apparent power. So now we have apparent power, which is 3750 VA, and using this information of apparent power, we can easily calculate what is our reactive power at load 1, where reactive power at load 1 or Q at load 1 is S sine theta. You know that Q is coming from the equation of VI sine theta. And at this part, you need to calculate what is the value of your theta. So your theta over here, okay, is calculated based on your power factor value. So here we use this theta, put it over here, you will get your reactive power. And remember that reactive power must be a positive value because of we have a lagging power factor over here. Here power factor is lag. Okay, that is for load number 1. Load number 2, we have reactive power of 1.6 kVAR or kVAR, kVAR. We have 1600 VARs, and remember that this reactive power must be a negative reactive power because in load 2 we have power factor, which is a leading power factor. And we try to apply the same strategy that we apply for load 1. Here we have S2 given by Q divided by sine theta. And remember, in order for us to get this theta value, you need to process first the power factor. And the power factor is given by 0.6, and take the arc cos of that, you will get your theta. Now S2, the value over here is 2000 based on this equation, and using this S2, the apparent power at load number 2, you can easily calculate your active power by using this equation. P equals to VI cos theta, or P equals to S cos theta. S, which means that we need to apply, or we need to use this S2 that we calculated earlier in order for us to get the P, or the active power. All right, and in order for us to get the total powers, AC powers in the circuit, please remember that the P total can be calculated or can be combined like this, where P total equals to P1 plus P2. Q total also can be combined like this, Q1 plus Q2. But remember that Q2 should be a negative value, and you will have your Q total as 650 bars, positive value. And okay, this one is very crucial. In order for you to get S total, you cannot just combine this S1 that you find here, 37050 plus 2000. You cannot do that. What you need to do is you need to use Pythagoras theorem. Based on these two values, you need to square it and take the square root of it, summation of the square root of it. Sorry, you need to square, sum, and then take the square root of it. in order for you to get the total apparent power. And for the total power factor, okay, again, total power factor, you cannot just combine 0.8 and 0.6 in order for you to combine the power factor. What you need to do is you need to take the total active power and divide it with the total apparent power you calculated over here in order for you to get your total power factor. And maybe you would wondering, is it the power factor lagging or leading? So how do we determine this is a lagging power factor? It is based on our Q value. Total reactive power that we have in the circuit is a positive value, meaning that it will be a lagging power factor. All right, any questions so far? Any question?
Okay.
Is it okay? All right, now, as I mentioned earlier in the class, if you look at our tutorial over here, okay, this part, the question number 2, definitely will be not in your test 2, okay, but maybe it will be available in final exam. But the question like this, question number 1, question number 2, is most likely available in your test number 2. And I really hope that you can take the opportunity of the tutorial session in order for you to get familiar with how do we combine impedance, how do we solve a circuit with a combination of series and parallel connection, and also use the source transformation theorem in order for us to proceed with the analysis. So that is very important. And I hope on Saturday, you will get, the results, the outcome will be a very positive outcome where you can, it's my ambition, my target is that all students will get full marks in test 2, but I don't know how it will turn up, but pray for full marks lah. Because in test 1, I don't know, maybe some of you guys still try to stabilize his knowledge in electric circuit analysis and try to get the catch up with the course. So that's why some of you guys cannot perform well in test 1. But I think in average, the marks is, I cannot find any student that can score 100% in test 1. So I'm hoping that in test 2, all of you can score good marks, if possible 100%. But I really hope that you can score good marks here in test 2, because you can bring all the points over here into your total or overall course grades. Anyway, that's I think that's the end of our tutorial session. And stop sharing first. Okay, as usual, if you have any question, you can ask later on in our WhatsApp group if you have. But if not, good luck for your final, not final exam. Good luck for your test 2 on Saturday, and hopefully you can score very good marks in test 2, and as well as for final exam in future. And I think next this week is not our final week meeting together. Maybe next week I'll try to we try to have one online session. Maybe we try to revise all the lesson that we learned, the topics that we learned previously, and I try to give you some useful tips in order to score in your final exam. Okay, in terms of marks, I try to give you the marks of test 1 and test 2 in next week class. So next week on Tuesday, I hope that we can meet again, and we will discuss about our results of test 1, and maybe I try to present also the answer scheme for you to do some revision later on in order to prepare for your final exam. Is it okay next week? Technically, we are finished over here. We finished our course. We have gone through 14 weeks, but I think I need to spend another one more session in order to, what do you call it, do some revision lah in terms of revise back what we have learned so far. Okay?
Okay, sir.
Okay.
All right. Okay, before we leave, can you turn on your camera so that I can take the snapshot of it. Wait, yeah. Okay, with that, I think that's the end of our course. Next week will be, as I mentioned, will be the revision week. We try to revise back what we have learned so far, and I try to give back your result for test 1 and test 2 next week. Only on Tuesday, because on Thursday we have public holiday, if I believe, in Malaysia. It's Thai Pusam. It's a public holiday in Malaysia. So on Tuesday we try to meet again, our last meeting. Hopefully last meeting lah. I don't want to see you guys anymore in next semester. next semester means that you fail this semester. Hopefully we
Don't feel me, Lotte.
try your best lah. Okay, try your best not to get failed. And actually, I really hope that you can score very good marks here in this course. Hopefully lah. Okay, try your best. Okay, with that, I think we end the session. Assalamualaikum. Goodbye.
Roger, please be generous.
Okay. Goodbye. Stay safe, everyone. Assalamualaikum.
Thank you, Lotte.
Thank you, Raja.
Thank you, Doctor.
Salam, Doctor. Have a good day.